If you've spent any time at all in the world of AI lately, you've definitely seen them.
Oh, yeah.
The big, scary terms of computer science: deep learning, neural networks, and then the really abstract ones like backpropagation, activation function,
Gradient descent.
gradient descent, exactly. And for a lot of us, seeing those words feels less like reading the news and more like walking into an advanced calculus class by mistake.
Well, that feeling is totally understandable, but I think it masks a very simple core truth.
Okay.
Deep learning, when you get right down to it, is just about learning through practice, through structured, continuous, and quantifiable feedback. It's really just the most sophisticated form of trial and error we've ever come up with.
Exactly. And that's our whole mission for this deep dive. We want to strip away that fear of the equations. We've gone through a stack of sources that make this whole thing incredibly accessible. And we're going to use one simple analogy for all of it. A basketball player trying to master the free throw shot.
The perfect analogy.
So we'll treat the neural network as the learner. It takes in some information, it makes a prediction that's taking the shot, it checks how wrong it was, and then it adjusts. Over and over and over.
Until the shot is perfect.
Right. You don't need to be a data scientist to get this. You just need to understand the mechanics of practice. Okay, let's unpack this.
And to start, we actually need to look off the court. We're in the preparation room.
Before the first shot is even taken.
Way before. Because the learning environment, the data, has to be set up perfectly. If the data is messy or inconsistent, the whole process fails before it even starts.
Okay, so that initial setup, it's all about turning real-world chaos into something a computer can actually use. So where do we begin?
We start with a concept called vectorization.
Vectorization.
Just think about all the inputs for a free throw. You've got, grip pressure, the distance from the basket, arm angle, the little flick of the wrist.
They're all just floating ideas almost.
Exactly. They're floating variables. And if you just throw that messy pile of raw observations at a network, it's completely useless.
So vectorization is the process of taking all that real-world detail and turning it into a clean, structured list of numbers.
A list of numbers.
It's like taking something qualitative and making it quantitative. It's like you're handing the player a set of flashcards where every bit of data is in the same place every single time.
Structure is key, you're right. But stability is just as important. So once you have that list, you need normalization.
Normalization. Okay, so what problem does that solve?
It solves the problem of unstable conditions.
Okay, give me an example of that in practice.
Well, imagine you're practicing free throws. One day, the ball weighs a perfect 1 kilogram. The next day, someone secretly swaps it for a 20-kilogram ball.
Okay, that would be a problem.
Right. And then the next day, it's back to 1. The player would have no idea what to fix. Is it their aim, their strength, their angle? The input scale is just, it's all over the place.
So normalization is about forcing all those different inputs, the distance, angle, whatever, into a comparable, standardized range.
You got it. We keep the values consistent. That way, when the model sees a number change, it knows that change is meaningful. It's not just random noise from a bad measurement.
So this whole preparation phase, the vectorization and the normalization, it really comes down to that iron rule of deep learning, doesn't it?
It really does. A great model has to start with great preparation.
Garbage in, garbage out.
Garbage in, garbage out. You can't learn a perfect shot on a court that keeps moving.
Okay, so the data is clean, it's ready. Now we can move into the mechanics of the learner, the player's internal technique. And this is where we get into parameters.
Correct. Parameters are the parts the network actually changes and optimizes over time. They are the core of what is being learned. And we usually split them into 2 key parts.
Weights and bias.
Weights and bias.
Okay, let's start with weights. I saw one source define them as importance settings, which I thought was really intuitive.
That's a great way to put it. Think about all those inputs we vectorized. Arm strength, jump timing, aim accuracy. As the player practices, they quickly realize that aiming correctly matters, well, exponentially more than how high they jump for a stationary free throw.
So the network literally increases the weight, the importance for the aim input, because that's the one giving the most useful information.
Precisely. The weights determine how strongly each input affects the final decision. Higher weight means more impact. Now, here's a little detail that trips a lot of people up.
Okay.
When training starts, weights don't start at 0. They typically start as small, random numbers.
Random. Why random? Wouldn't that just make things chaotic at the start?
It sounds counterintuitive, I know, but it's crucial. It prevents what's called symmetry. If every skill pathway started with the exact same importance 0, they would all learn in the exact same way.
Ah, so there'd be no reason to prefer one skill over another.
None at all. They'd all adjust identically. Randomness encourages different pathways to develop right from the start. It leads to a much richer, more effective network.
That makes a lot of sense. It lets the network explore. Okay, so that brings us to the second parameter, bias. If weights are about relative importance, what is bias doing?
Bias is like the player's natural baseline style. It's a built-in offset, totally independent of the current data.
So, like, maybe a player just naturally shoots a little bit higher than average.
Exactly that. Bias is that adjustable default tendency. It gives the network the flexibility to shift the final output up or down, no matter what the inputs are. And while weights start random, bias often just starts at 0 and gets adjusted from there.
Okay, so we have our clean data and we have the player's adjustable technique, the weights and the bias. But the network needs some kind of filter, right, to make complex decisions. It needs a non-linear brain,
And that's the job of the activation function.
the decision filter.
This is the concept that often feels the most abstract to people. They think, well, computers are just calculators. Why do we need this special function?
And the simple answer is, without it, the model is stuck making simple straight-line calculations.
But the real world and winning basketball games is not a straight line.
Right.
Exactly. That nonlinearity is the secret sauce. The activation function lets the network model these complex, curved relationships. It lets it realize, okay, if my wrist angle is just right, it's a swish. But if it's even 1 degree off, the whole thing changes dramatically.
A linear model could never capture that kind of nuance.
Never.
And this is where we get those code name sounding functions. ReLU, sigmoid, ton.
Right, but if you translate them into plain language, they're just simple rules.
Okay, so let's take ReLU, the rectified linear unit.
The rule for ReLU is basically, if the calculated effort is a positive number, pass it forward to the next layer of thought. If it's 0 or negative, just stop it right there.
So it's a simple on-off switch for a thought process?
A very efficient on-off switch. And then you have sigmoid, which is great for a final decision. It's the player asking, is this shot more of a yes, it's going in, or a no, it's going to miss? It just squashes the answer into a probability between 0 and 1.
And the last one? Ton.
Ton, or hyperbolic tangent, is similar, but it gives a range of confidence between -1 and +1. So it lets the model be more certain or uncertain, not just stuck between absolute yes or no. This filter is what lets the network really problem solve.
It's pretty amazing. All that complexity just to decide whether to pass an instruction on. Okay, so the network is prepared, the internal technique is set, time to get on the court. Here's where it gets really interesting.
This is the action loop, and it all begins with forward propagation.
Which is just taking
Yeah.
the shot.
It's just the player performing the task. They're using their current technique, their current weights and bias, to take a shot.
So in the network's terms, that's the whole flow. You take the clean inputs, you apply the important settings, the weights, you add the natural offset, the bias, you run it through the decision filter,
The activation function.
and boom, an output is produced. The predicted path of the ball. Forward propagation is the attempt.
But an attempt is only useful if you measure the result. That's the job of the loss function.
The scorecard.
The scorecard. It quantifies the difference between what was predicted and what actually happened. Did the ball hit the rim instead of swishing? The loss function turns that mistake into a single number.
So a high loss number means a bad miss. A low loss number means you were close. The sources really emphasize something called cross-entropy loss.
Yes. That's a fascinating one because it heavily penalizes confident wrong answers.
What do you mean by that?
Well, if the player is absolutely certain their technique is perfect, but the ball misses the entire backboard, the model learns a much harsher lesson than if it was uncertain and missed by just a little.
So the key here is that loss isn't a punishment. It's just information.
It is high-fidelity information about what went wrong, and the network uses that information to get better.
So the network has its attempt, and it has a score for how badly it failed. How does it trace that error back to figure out what to fix?
That is the incredibly heavy lifting of backpropagation.
Okay.
Think of it like a coach rewinding the play in super slow motion. The coach doesn't just say, you missed. They say, your elbow flared out at the exact moment of release, and that changed the final angle.
So backpropagation is the math that figures out exactly which weight or which bias was most responsible for that final error score.
That's it. It efficiently calculates the gradient, the slope of the error, for every single parameter. It traces that loss number all the way backward through every decision filter to find the cause.
It knows what to adjust. But I assume it doesn't just randomly change everything. It needs a strategy.
And that strategy is gradient descent. This is the continuous practice loop, the micro adjustment.
Okay, so let's connect the dots. The player shoots,
Forward propagation,
measures the error.
loss function.
Backpropagation tells them what caused the error.
And gradient descent tells them how much to change those things to do better next time.
It sounds like trying to find the most efficient way down a mountain in the fog. You want to take steps downward, but you don't want to jump off a cliff.
That is the perfect analogy. You want the adjustments to be methodical. If the adjustments are too big, that's what we call a high learning rate. The player's technique just becomes chaotic. They keep overshooting the best technique.
And if the steps are too small, progress takes forever.
Exactly. So gradient descent is that core strategy that ensures the system is always moving toward a better, more optimized shot.
In that distinction, between what the player learns and what the trainer sets up,
Yeah.
it's so important for understanding where the human control really is. Let's clarify the difference between parameters and hyperparameters.
Yes. This is a vital point for anyone listening. Parameters, the weights and biases, are learned during training.
Okay.
They are the internal settings the network modifies itself based on all that feedback, like the precise wrist flick intensity.
They're dynamic. The network is figuring them out on its own.
Correct. Hyperparameters, on the other hand, are chosen. They are settings that guide how the training happens. The developer, the human coach, decides these beforehand.
Like deciding how many practice shots to take. That's the number of epochs, right?
Exactly. Or setting that critical learning rate we just talked about, how big the adjustments can be. Even the number of layers in the network, the complexity of its brain, that's a hyperparameter.
So parameters are learned, hyperparameters are chosen. The human is still the coach, setting the rules of the practice session.
The human is very much still in control of the environment.
Seeing it all laid out like this really brings the whole picture into focus. You have the initial data prep,
Vectorization and normalization.
which feeds into the adjustable technique of weights and bias. The attempt is forward propagation. The feedback is the loss function and the learning. The real learning is back propagation with gradient descent.
It's one seamless, optimizing loop, just running thousands, millions of times.
So what does this all mean when we step away from the basketball court and look at the AI tools we're all using every day?
It means that every single time you use a generative AI or a search engine predicts what you're typing, that model has gone through this exact cycle billions of times.
Well, it's all trial and error.
It's highly optimized trial and error. By turning the complex world into clean numbers and giving the network clear rules for adjusting itself, it can achieve incredible performance on tasks, whether that's syncing a free throw or translating a language or writing code.
There was a critical reminder in the sources, though. A model can't learn what it can't see. If you forget to include the distance to the basket as an input, the network can train forever, and the ball will never go in.
A very important point.
So here's something for you to mull on. Given how absolutely crucial that initial data preparation is, and that the whole process starts with those initial weights and biases,
Yeah.
how much of a neural network's final capability is decided, not by the network itself, but by the human who decides which inputs to vectorize and include in the first place. Is the quality of our AI really determined more by our selection of data than by the training itself? Think about that selection process the next time you interact with an AI.